Great. Thank you for the introduction and thanks for the invitation to speak. So I'm excited to tell you about tensor decompositions and their applications. So I'll be surveying how tensor decompositions play a major role in learning latent variable models that are important both from a machine learning and data science perspective, and also have some pretty wide-ranging applications in the sciences. So this is meant to be a sort of gentle introduction first to tensors and to some of the key algorithms for dealing with tensors before I explain how exactly they have such a myriad of applications. So one of the funny things is that when you talk about algorithms for tensor decompositions, these things actually are studied across many different communities. And at some point, I got really interested in trying to dig into the history of these things because the particular algorithm that I'll be focusing on that'll enable all of the different exciting applications is actually something that by my count has been rediscovered across 5 or 6 different communities spanning multiple decades. So I want to tell you a little bit about, where this algorithm comes from. And the way that I think about it is it's really a very natural ingredient in a story that comes from factor analysis. So some of the first people to, work with tensor decompositions and introduce some of the basic algorithms that we're going to be relying on were people who worked in the psychometrics community. And let me tell you a little something about, why they were interested in tensors in the first place. So back in the 1900s, in the early 1900s, Charles Spearman was a very famous psychologist, and he had the following postulate. So he believed that there were fundamentally 2 types of intelligence: educative and reproductive. Now, what this means is that he believed that intelligence was divided into these 2 categories, where the first is the ability to make sense out of complexity, and the second one is the ability to store and reproduce information. Now, the truth is that this is a very simplistic model for intelligence, but what I'm more interested in is how he went about trying to prove this hypothesis, because this was the first place in which factor analysis was used. So what he did was he took a collection of data, which for him was scores of 1,000 different students on 10 different tests. And what he believed was that this matrix, where the entry in row I, column J, is just the numerical value of how student J did on test I. What he believed was that this matrix could be approximately represented as the product of 2 other matrices. And the critical thing was that this first matrix A has only 2 columns, and the second matrix B transpose has only 2 rows. So what he believed was that this hidden decomposition would tell you for each test, the corresponding row in A, would tell you to what extent that test tested these 2 different modes of intelligence. And each column in B transpose would tell you for each student what their abilities were in these different modes of intelligence. So here, the inner dimension of this factorization that he was looking for was 2. Now, there's a big problem with trying to do factor analysis with matrices, which is really where tensor decompositions are going to save us. Because one way to think about what's going on is that on the left-hand side, we have access to either an approximate or an exact matrix M that we hope can be written as the sum of AI tensor BI. And we can write this in matrix form as this A times B transpose matrix. And somehow the hope is that we can take this left-hand side, which we can measure from our data, and maybe we can find these correct factors that when we look at them, we can see that Spearman's hypothesis is indeed supported by the data, that there really are these 2 different modes of intelligence. So the basic question that we're now faced with is a uniqueness question. Because even if we have access to the left-hand side, and even if there is some nice correct factorization that writes M as A times B transpose, who's to say we can find it uniquely? So that's the important thing, is that the big problem is what's called the rotation problem in factor analysis, which is even if there were a correct factorization of M into A times B transpose, what I can do is I can take any invertible matrix R, and I can put R and R inverse in there, and I can group together A times R to create a new matrix, and I can group together R inverse times B transpose to get a new matrix as well. And this would be another perfectly good factorization that has the same inner dimension, but it might obfuscate the things that we're looking for, this representation in terms of these 2 hidden modes of intelligence. So what I claim is that when we ask this problem in the context of matrices, the answer is pretty hopeless. Because in general, these factors, the A sub i's and the B sub i's, they're just not determined uniquely in any reasonable way unless we have ridiculously strong assumptions about them. So for example, when would the AIs and BIs be uniquely determined, at least up to some trivial rescalings? Well, you could have a property that the AIs and BIs are orthogonal, in which case you could find the factorization through the singular value decomposition. Or alternatively, you could have the property that the rank of the matrix M is 1, which is really the same thing as the previous one. And so this is called, as I alluded to, the rotation problem. It really stems from the fact that when we want to do factor analysis on real data for scientific purposes, for data science purposes, for machine learning applications, well, the matrix decomposition is just not unique enough for our purposes. So dealing with this major barrier was what motivated people in the psychometrics community in the 60s and 70s to introduce the study of tensor methods, was because, as we'll see, they are unique under much more tame conditions. And in fact, they come along with algorithms for even finding the decompositions. And that's something called Jennrich's algorithm. That'll be the first part of my talk. That's the thing that, by my count, has been rediscovered many, many times. So what I want to do in this tutorial is explain how beautiful this simple algorithm is, and then show you how to redo some of the exciting applications that were done through tensor methods just using Jennrich's algorithm as our main building block. Now, again, please stop me anytime with questions. So let's start off with Jennrich's algorithm. So in the context of matrix decompositions, we have on the left-hand side this matrix M, which we think of as something that comes from our data. And we want to write it as the sum of, R rank 1 matrices, so AI, tensor, BI. And tensor decompositions, well, they work in the same way, is that you have a tensor, which is now, instead of a two-dimensional grid of numbers, it's a three-dimensional array of numbers. So it's indexed by I, J, and K, let's say. And the way that you think about tensor decompositions is, first, what is a rank 1 tensor? Well, I can take a vector A1, a vector B1, and a vector C1, and I can take their tensor product. In particular, what that would mean is that would construct a new tensor that's rank 1, where the ijk entry would be the product of the ith entry of the first vector times the jth entry of the second vector times the kth entry of the third vector. And then in general, when I give you a tensor that has rank larger than 1, what you want to do is I give you the left-hand side, and you want to be able to figure out the right-hand side. You want to be able to write it as the sum of not too many rank 1 tensors. So this is the basic notion of what a tensor is, which you've seen many times already in the tutorials that people have given. And this is also, the notion of the rank of a tensor is, can you find this decomposition on the right-hand side? So the thing that I've been alluding to is that tensors are going to save us. Because really what we care about is, when are tensor decompositions unique? And they're going to be unique under much tamer conditions than for matrix decompositions. So let's talk about that. And this is Jennrich's algorithm. So imagine that I give you a set of factors, A sub I, B sub I, and C sub I, and they have the following conditions. First, the collection of vectors for the A sub I are linearly independent. Same thing goes for the B sub i's. They're all linearly independent. And then you can actually afford a slightly tamer condition on the CI's. You can just require that there's no pair of vectors in CI that point in the same direction. So there's no pair of vectors in CI that are scalar multiples of each other. Then if I consider a low rank tensor, T, which is the sum over I of AI, tensor BI, tensor CI, then what I claim is that the tensor decomposition is unique under these linear independence conditions on the factors. Now you have to be a bit careful. First of all, what does it mean to be unique? Now, there are always some trivial things that you can do. See, we have the left-hand side, the tensor T, and we want to figure out the right-hand side and understand whether the right-hand side, that decomposition, is unique. Now, there are some trivial ways that you can change the right-hand side without really changing anything, which is, for example, I could permute the rank 1 tensors that show up on the right-hand side. So I could swap the A1 tensor B1 tensor C1 term with the A2 tensor B2 tensor C2 term. That doesn't change anything. And the other thing that I could do is I could rescale some of the factors so that none of the rank 1 terms change. For example, I could double A1 and then have B1. And that wouldn't actually change what the rank 1 tensor is in the tensor decomposition. But subject to those changes, the tensor decomposition is unique. So it's unique up to permuting the rank 1 terms and rescaling the factors. So equivalently, the way to think about this is that the rank 1 factors in the minimum rank tensor decomposition are themselves unique. And one of the funny things, as I alluded to, is that this algorithm seems to have been somewhat forgotten in the literature. So Jennrich's algorithm, at some point I got kind of obsessed with trying to figure out historically where this algorithm first appeared. And eventually I traced it to the 1970s, where it appeared in a paper of Harshman, and it was credited to someone named Dr. Robert Jennrich. Now, one of the things which was forgotten about this was that, see, the people in the psychometrics community, they cared a lot about the uniqueness of tensor decompositions. And Jennrich showed a very powerful uniqueness theorem for when tensor decompositions are unique. But later on, Kruskal showed a stronger uniqueness theorem that just happened to not come with an algorithm for computing the factors. So after Kruskal's paper, people forgot about Jennrich's algorithm. They forgot that even though Kruskal's uniqueness theorem was stronger, well, Jennrich's at least came with an algorithm. So over time, people in statistics and computational biology and theoretical computer science and machine learning all discovered this one simple algorithm that I'm going to show you. So one thing that I want to comment on is that if you think about the conditions in Jennrich's algorithm, well, if I have a tensor T that's n by n by n, then what's the best possible scenario where this theorem could apply? Well, I need that the factors a sub I are linearly independent. So the rank R that I can tolerate is at most n for this type of algorithm. Kruskal's uniqueness theorem works up to some constant times n. And even though tensor decompositions are unique under even the rank being up to n squared, a constant times n squared, we don't know of any algorithms for dealing with that. And there's some relationships to computational complexity theory that we can take offline. So let me tell you Jennrich's simple algorithm. I remember I had to jump through quite a few hoops to find this paper. Very hard to find. But sitting in the middle of this paper from the 1970s was this short one-page proof of this algorithm, and it's beautiful. So I give you this tensor T. How am I going to find these hidden factors under the conditions stipulated by Jennrich's theorem? So the first thing that you're going to do is you're going to take your tensor and you're going to squash it into a matrix. In particular, what you're going to do is you're going to choose a random vector x. Just for simplicity, let's assume that the tensor T is n by n by n. So my vector x is a dimension n vector. It's random. Maybe random from the unit sphere suffices. And what you're going to do is you're just going to add up these different matrix slices through the tensor, weighted by the different entries of x. So in particular, why this is a nice operation is because if I do something really simple, like I have a rank 1 tensor, which is A, tensor B, tensor C. And I don't know what A, B, and C are. I just have access to the left-hand side, which is T. What happens when I take this tensor T and I hit it with this vector x and squash it down to a matrix? What I claim is that you get a rank 1 matrix. So I started off with a rank 1 tensor. When I hit it with a vector in this way, I don't increase the rank ever. And what I'll get is a rank 1 matrix, which looks like A tensor B times a scalar that depends on the inner product between C and X. So that's the important thing. And in fact, if I had a rank R tensor, well, if I hit it with some random vector x, then I'll just get a matrix that's rank at most R, because I can just add up all of these contributions from the individual rank 1 terms, even though I don't know them. So in particular, what I claim is that even though we don't know what this decomposition is, we can keep track of how the operations we're doing on the tensor, well, what they're algebraically doing to the factors that we want to find. So in particular, I don't know these a sub i's, the b sub i's, the c sub i's. They satisfy the conditions stipulated in Jennrich's algorithm. But when I hit t with x, I get this particular matrix that I've written it out so that it's very clear its rank at most R. And in particular, under the conditions in Jennrich's algorithm, it will actually be rank R almost surely. So x here, as I mentioned, is chosen uniformly at random from the unit sphere, just for simplicity. So now I can write this in a slightly different way, which is I can take my factors, the a sub i's, and I can organize them into a matrix so that they're the columns of a matrix A. I can do the same thing with the factors b sub I. I organize them into a matrix where the columns of B are the B sub i's. And then I can organize these scalars that I'm supposed to multiply into a diagonal matrix. So it's a diagonal matrix where along the diagonal, it just has the inner product of C sub I and X. So I'm going to write D sub X just to denote that this diagonal matrix is a function of my first choice, this vector X. So this is great because now what I can do is I can do the same thing again, but with a different random vector Y, again chosen at random from the unit sphere. And I get the same thing. It's a matrix. And in terms of the things that I want to solve for, these unknown factors, I get A times the diagonal matrix times B transpose. There's only one difference here, which is that the diagonal matrix has changed. Because now the diagonal matrix has along its diagonal the inner products between the C sub i's and the Y. And now comes the magic is, matrix decompositions weren't unique, right? That's what we talked about with the rotation problem. And here I'm taking my tensor and I'm squashing it down to 2 matrices. But uniqueness is going to work for 2 matrices. So in fact, all of these tensor methods are really generalized eigenvalue problems in disguise. That was hiding within Harshman's paper. So let's see how this works, as if I take this matrix, which is formed by hitting t by x, and the matrix formed by hitting t by y. Let me make my life simple. All of these things generalize, to cases where you can't take inverses and you take pseudo-inverses instead. But let me assume that all of these matrices are invertible, just to make my life easy. Well, what's going to happen is when I take tx times ty inverse, well, I can just, even though I don't know the A matrix, the dx matrix, the B, and the dy, I can algebraically figure out what it looks like. And now things become nice because the B transpose and the B transpose inverse go away. And I get A times dx times dy inverse times A inverse. So now this is exactly what we're looking for, is this is an eigendecomposition. In particular, I can construct this matrix t hit with x times t hit with y inverse. And the unknown factors that I'm looking for are exactly the eigenvectors of this matrix. And eigendecompositions are unique under fairly tame conditions. What do I need in order for the eigendecomposition to be unique? Well, it suffices to have all of the eigenvalues be distinct. So the eigenvalues are exactly what happens in this diagonal matrix, dx, dy inverse. So remember that as long as the C sub I factors have the property that no two are scalar multiples of each other, you can check that almost surely all the entries in this diagonal matrix, dx, dy inverse, will all be distinct. So now we're great. Now that only recovers the factors a sub I. You can do a little bit more work. It's not that surprising. But what you can do is you can take a different expression, ty times tx inverse. And if I've done this right, then the eigendecomposition of that matrix gives us the factors b sub I. So then I found the A sub i's as an eigendecomposition. I found the B sub i's as an eigendecomposition of something different. And all that remains is to match up the A sub i's and B sub i's and solve for the C sub i's. So what I claim is you can match up the A sub i's and the B sub i's because they're actually eigenvectors whose eigenvalues for these two eigendecomposition problems correspond to reciprocals of each other. So once they're distinct, the eigenvalues in this eigendecomposition, I can match them up uniquely. And now all I have to do is find the C sub i's, and that's a linear system. So this was what was buried in Harshman's paper that people, actually myself included, rediscovered many times. That's maybe why I got obsessed with trying to find the actual place where this originated. So now let's go back to the story from Spearman's hypothesis, which is really the genesis of factor analysis. And let's see how tensor decompositions are going to save us here before I start to survey some of the wide-ranging applications of tensor decompositions. So remember that, if I'm given the left-hand side, this matrix M, and I want to find this hidden factorization, the one that when I look at, I can scientifically say, aha, that's the right one. The problem was that I needed very strong conditions on the factors to do it. But now if instead I had a tensor, then we can ask the same question, when can I find these factors, the A sub i's, the B sub i's, and the C sub i's uniquely? Jennrich is telling us that you can find them under the condition that the A sub i's and the B sub i's are full rank, and there's no pair in the C sub i's that are scalar multiples of each other. And even better, there's actually an efficient algorithm just based on eigendecomposition that does the trick.
We have one question by raised hand by Joseph Landsberg. Let me
please
unmute him. So hopefully, so you should be able to mute now. Yeah.
Hello, I have your book.
Yeah, and it's good to see you again. I have actually several questions. First of all, what happens if you think you have a tensor of rank R, but it has higher rank and you attempt to do this algorithm?
So that depends. That's a very interesting question. Now, if the rank is, let's say, less than n, that you think it is, so you think it's less than n, now, under some tame conditions on the tensor that it really is and its tensor decomposition, you would end up getting too many non-zero eigenvalues in the eigendecomposition. Or the matrices that you would have would actually be invertible, whereas you're supposed to actually have to take the pseudo-inverse.
Okay, but let's say R equals n.
Mm-hmm. Then, things could go wrong.
And so I was wondering if you could sort of use this to certify somehow, at least with high probability, that a tensor indeed has rank strictly greater than n.
Yeah, so that's a great question. So I'm going to give you a short answer, but then I think we should take it offline because I don't want to derail too much.
Okay.
So, in your book, you have this thing called Young flattenings, right? Which there's some pretty interesting connections between, Jennrich's algorithm and other methods for certifying rank lower bounds. So one of the things actually that my student showed in her thesis about a year ago was that you can use some of these techniques from matrix multiplication lower bounds to show that in some types of nice models for low rank tensors that you can certify and correctly determine what the rank of the tensor is up to 2 times n. But beyond that, some of the obstructions in terms of proving lower bounds better than, some constant times n seem to have some relationship. So on the one hand, what's kind of interesting, although it's not going to be the subject of this tutorial, is that to a certain extent, you can study one model, which I'll call smooth analysis for tensor decompositions, where you just assume some type of genericity condition on the hidden factors. There, the best known algorithms for either decomposing or certifying the rank all seem to crap out at like C times n for a third order n by n tensor. Whereas if it were actually a random tensor with random factors, then there are methods based on the sum of squares hierarchy that can work up to n to the 3 halves but that seems to be the limit from connections to random CSPs. Okay. But maybe we can take such a technical thing offline, because I don't want to kill people with
yeah, we can talk more about it later. But one other question, though, and maybe we'll have to take this one offline as well, is what if you have a tensor that has border rank R, but rank strictly greater than R, and you attempt this algorithm?
That's a great question. So I'm not sure, let's maybe talk about that one. I'm trying to keep it very simple. So sorry, I'm going to say only easy things for now, but I'd love to talk to you afterwards about that.
Okay, we can talk after your talk.
Sorry. It's so much easier when we don't have things on Zoom, because then I can look around the audience. I can see if I'm killing the audience with too much technical stuff. I went from last semester teaching an undergrad class to this semester teaching an advanced grad class, and it's quite a whiplash. So I'm somewhere in between right now. So let me at least tell you, because I think this is kind of the fun. Are there other questions that I should answer right now? Because this is a great juncture for questions before I talk about applications. I see more in the...
I don't see any other hands raised or in the chat.
I have a follow-up.
So please continue.
Okay, all right, so let's do this. Again, trying to keep it simple. So let me tell you about some beautiful applications. This is, yet another place where tensor decompositions were rediscovered, especially the algorithm. And, one of the places where I'd learned about it was in phylogenetic reconstruction, where it's called Chang's lemma. But this is a beautiful problem in its own right. So let me tell you about a cool application of tensor decompositions, in particular Jennrich's algorithm, to phylogenetic reconstruction. So there's this beautiful model which asks to try and find, it's a very well-defined statistical model, which I'll explain. But the goal you can think about is, we have all of these living species. These are the extant species. And maybe we can sequence their genomes, and maybe we can even align their genomes so that we have an idea about, how the different characters align. That's a big assumption, but just bear with me. Then one thing we might want to do is compare these aligned genetic sequences to try and reconstruct the tree of life. Namely, where there were speciation events, where different things diverged, and also among the extant species, how they're related to each other in this tree of life that we wish we had. So let me tell you about the following statistical model. So there's some underlying tree structure. The green circles denote the extinct species. The red ones denote the extant species. And what's going to happen is that this process will describe on a symbol by symbol basis what happens. So we have some alphabet sigma, and then at the root of this phylogenetic tree, we sample from some initial distribution. So it just samples one of the symbols in sigma. And then what's going to happen is along each one of the edges in this tree, there's a matrix that describes the conditional distribution. So it's really a size of sigma by size of sigma matrix. And if you tell me the symbol at Z, then when I take an indicator vector for that symbol being there, and I multiply it by this matrix, I'm going to get what is the conditional distribution on what the symbol is that occurs at this corresponding red node B. So what this process looks like is in each sample, we observe a string whose entries come from this alphabet sigma, but the catch is that we only observe it on the extant species. And the idea is that we want to take many samples from this process, which corresponds then to, for each species having a long string of what its genetic sequence is, and then use that joint information to try and recover what the tree is, and even a description of what the conditional distributions along each one of these edges look like. Because those are the types of things that might tell us how long were these evolutionary branches. So this is a very natural model in population genetics. It's a standard one. In fact, it's related.
Sorry for interrupting. We have a couple of questions here.
Please go ahead. Yeah.
And I think I have messed up a little bit with the chat. So the first one is from is, do we know how to de-randomize Jennrich's algorithm? And there is a second one, and try to group them together from Alex. It's in the matrix case, getting the rank right in factor analysis doesn't seem to be a big problem in applied data analysis. There is a reference. I'd be curious if something similar holds in applied tensor.
Okay, so so the de-randomization is an interesting question. This is just off the top of my head, but I think if you have stronger conditions on the C sub i's, more than just this no2 or scalar multiples of each other, then you don't need this sort of random choice of X and Y, because deterministic choices will work for these things. But I'll have to think a little bit about that. Certainly, the naive implementation of Jennrich doesn't seem to me to have a very clear de-randomization. Now, the second question was what? That could you repeat it again?
Yeah, the second one was dealing with the that getting the rank right in factor analysis for matrices is not a big problem, but is something similar holds in applied tensor factor.
Yeah, I think first of all, it's way more subtle for tensors because, you know, for matrices, you have the Eckart-Young theorem. So even if I don't know what the rank is, I can just plot the singular values, and usually there's sort of an elbow effect, and I can figure out where to cut it, and it's not a big deal. But the algorithms for tensor decomposition, they much more strongly use the fact that the tensor is actually very close to being the rank that it says it is. So really, the stuff that I'm hiding from you is the fact that in order to apply tensor decompositions like Jennrich's algorithm to statistical models, you never exactly have the left-hand side, the tensor. Those are moments from your distribution. At best, you get very good estimates for it. And what you really need is not just Jennrich's algorithm, but you need a stability analysis. Now, with standard tools in numerical analysis, you know, there's a book by Stewart and Son about stability of the generalized eigendecomposition. You can get those things to work out, but as soon as you add some sort of, you know, other terms to your tensor where the sort of injective norm for those things is pretty large or is not too small compared to the sort of signal you're looking for, then these problems actually become computationally hard once again. So once again, I'm trying to not answer this with too much baggage because I haven't told you what the injective norm is, but people seem to be asking questions about a tutorial that is more advanced than the one I'm giving. Any more questions?
Yeah, there is another one. Are there any extensions beyond 3 modes for Jennrich's algorithm?
Yeah, so the extension beyond 3 modes is pretty easy for some of them. So for example, if I had a 5-mode tensor, what I could do is I could just, you know, if it's an n by n by n by n by n tensor, I could just reshape it so that's an n squared by n squared by n tensor. And then the important thing is that this rank condition is now going to hold. You know, I mean, you will be able to work with Jennrich's algorithm even when the rank is up to n squared, right? Now, if you wanted to work with 4th order tensors, there's a beautiful algorithm called Fubi that does the trick. So there are a lot of different ways to do that. I'll tell you a little bit about some of the higher order tensors later on when I talk about applications to mixture models. That's one place where they show up. But, you know, once I show you some applications of tensor decompositions, what'll be clear is that in some applications, the upper bound on the rank that we can tolerate has some implications for an upper bound on, you know, the number of factors or components we can use it to learn in different mixture models.
Okay. I think that's it. Thank you.
Okay, sounds good. All right, so we have this phylogenetic reconstruction problem with the tree of life. Now that's just motivation. Really, it's a very simple statistical model because we're getting some sort of word on this alphabet sigma, coming from the stochastic model where we start with some distribution on the root, and then we propagate it with these transition rules, these matrices R that happen along the edges of our tree. Now, for those of you who are more interested in data science and machine learning, actually this is very related to algorithms for learning hidden Markov models, because you can do the same thing A hidden Markov model is basically the same model, except for the fact that it's on a very simple tree. It's on a caterpillar graph. Because what happens is that you have some initial distribution on this hidden state, and you can have some different alphabet sigma sub s that represents the hidden states along the backbone. And then you might have some different alphabet sigma sub o that happens along the observed nodes, which you see. And once again, you have these observation and transition matrices that describe the conditional distributions. When you tell me the hidden state at some node, what is the conditional distribution on the symbol I see? And also when I tell you the hidden state at some previous hidden node, what is the conditional distribution on the hidden state of the next hidden node? So in fact, in each sample we observe, we just get a collection of these observed symbols from the sigma sub o alphabet. And this is really the same model in disguise, except for the fact that I know what the underlying tree is. It's always a caterpillar graph. But let's solve both of these problems at once using Jennrich's algorithm. Okay, so actually I'm going to take a little bit of a detour just because it's fun. So I'm going to tell you something about the phylogenetic reconstruction problem. That's not explicitly about tensors, but it'll tell you how we're going to be able to reconstruct the topology. That's the first problem we have to solve in order to solve this phylogenetic reconstruction problem. That's not a problem for the HMMs, because in the HMMs you assume that you know the topology. But this is a fun detour anyway, so it'll sort of complete the story. One of the first questions you can wonder is, you know, I give you this configuration of symbols along each one of the extant species. Can I reconstruct the topology of the tree from random samples? And then I'll worry about finding the transition matrices later, and that's where Jennrich's algorithm is going to save me. So usually what we assume in these types of models is that each of these transition matrices along the tree are actually full rank. And what that means is that the root is arbitrary. You can actually reroute the tree to any node you like, which will be helpful for our purposes. And then there's a beautiful work of Steele back in the mid-90s, which showed the following. So if you look at two different leaves, so extant species X and Y, we can look at a matrix that describes the joint distribution on their symbols. So to be clear, this matrix P sub XY is a size of sigma by size of sigma matrix. That's something that you can compute very easily from your samples because it's just moments. And what he showed is that if you take this crazy expression on the right, where you have, you know, something that depends on the determinant of P sub XY, and there are also some probabilities associated with the marginal distribution on X, on which symbol it takes on. Well, if you compute this right-hand side, then that'll give you, that's the way that I'm defining this D sub XY. And what Steele showed was that this expression is a distance function along the edges of the tree. So you can actually compute this distance function in principle, even for things you can't observe, for X's and Y's that are adjacent in the tree. And then you get some distance along the edges, dxy. But if you compute the distance between two different things that are not connected by an edge, but are connected by a path, then their distance, which you can now compute, will be the sum over the edges in the path that connects them in the tree of this dxy function.
I have, hello, we have another question here from Landsberg. Let me just unmute him.
Yeah, this is a naive question. Can you go back to the caterpillar thing?
Yes.
Yeah, so physically, what is this, these O matrices? Where do they come from just in science or something?
Yeah, so this would be more in engineering applications. One of the places where HMMs show up is, for example, in speech recognition. Because then you could imagine that maybe the hidden state represents like what kind of phoneme I want to say in some sort of sequence. And then these observed matrices represent something like how that's actually mapped to a waveform. So that would be one way that these things show up. They also show up in different kinds of sequence and text analysis types of things. Because, you know, maybe you want to use them to translate between different languages. So you can think about, having some sort of, hidden state that represents something about what you want to say in the sentence in some little window. And then the observed matrices might represent, the way that's translated to an actual instantiation into a language. But when you train these kinds of models across two different sequences, they can give you ways to sort of map from one language to another. These are not the most advanced language models, but they're actually one of the building blocks of even pretty sophisticated things that we do now.
Thank you.
Okay, so Steele introduced this function, d sub xy, and you can define it for any two nodes, x and y, that show up in your tree. But when the x and y are extant nodes, you can actually compute what dxy is because I know everything on the right-hand side. And what he showed is that this is a distance function in the sense that the distance between two leaves is the sum of the distances along the edges in the unique path that connects them in the tree. And if you have intuition for this and you see it immediately, more power to you. I don't. It's something you can check, but it's not even obvious that it's non-negative, but it is. In any case, once you have this distance function, you can actually reconstruct the topology of the tree pretty easily. Because if the transition matrices are full rank, then the distance function is never zero, so it's always strictly positive. And then imagine that you have four different extant leaves, right? So you have these four different nodes, A, B, C, and D. If you think about connecting them with paths, how you connect them with paths to each other in the tree, there are a few different induced topologies that you can have. Because it could look like, when I trace back the path between A and D, they merge first, and then they go on to B and C where they split. Or it could happen that A and B merge first, and there's one other possibility too. And what you can show is that if you can query all of these different pairs of nodes, what the distance is between them, then you can decide which of the induced topologies it is. So this is kind of not hard to see because in this left-hand side, that edge that connects the AD subtree to the BC subtree, well, that edge has some positive distance. So you'll see based on, where the minimum distances are and how they're organized, how to reconstruct the topology of the tree. In fact, if you do even more work, you can actually bound the sample complexity. So how many samples do you need to get good enough estimates to the distance function so that this quartet test allows you to piece together for any four nodes what the induced topology is, which then you can use to figure out the overall topology of the tree.
We have another question here from Jordan Ellenberg. Is the distance function on the previous slide equal to the path distance on the tree, or is it just monotone in that distance, or for some reason so you can use quartless test, or meaning Steele's distance at ultrametric?
Let me see if I can answer that. So here what I'm talking about is that dxy is going to be something that can be defined for any pair of nodes in the tree. So even if they're things that I can't observe, like, there are two adjacent nodes in the tree, which are both extinct. That stochastic model defines some joint distribution on their symbols, and there are some marginal distributions on their symbols. So I can certainly, in principle, if I had it, which I don't, I could compute the right-hand side. And what turns out to be the important thing is that if you take any two nodes, even ones which are not adjacent to each other in the tree, x and y, well then if you compute this distance function a la Steele, dxy, that depends on their joint distribution, then it actually will have the property that it is literally the sum over the edges of the distances according to Steele's distance function along the unique path that connects them. So one way to think about this is that, when I can reroute the tree arbitrarily, if I reroute it at some node x and then look at the transition rule that takes me to y, I'm going to get a product of these stochastic transition matrices along the path. And so that first term, this natural log of the determinants, is going to work out exactly the way it's supposed to, because the determinant of the overall transition matrix will be the product of the determinants of each one of the individual transitions. and then the natural log will mean that they add together. So in fact, the natural graph theoretic distance between the tree, the nodes within the tree, is sort of not meaningful in the phylogenetic reconstruction problem. It's really Steele's distance function that tells you how long and short the edges are, that tells you sort of the natural geometry to work with.
I have a hand raised by Dimitri. I'll let him ask the question.
Thanks. Sorry, just a quick thing. So there's no typo, right? There is the very last minus sign is a minus, right?
Yep. So you need this for some sort of telescoping contributions, but it really is a minus.
Okay, thanks.
So in any case, what I was sketching out was this, algorithm of Erdos et al., which uses Steele's distance function, the fact that it's a distance function, along with quartet tests, to be able to piece together for any 4 nodes what is the induced topology, from which it's not hard to see that you can reconstruct the entire topology. But now enter tensor decompositions. So what we want to do is, once we know the topology, which we took for granted in the case of HMMs and is an interesting question in the context of phylogenetic reconstruction, the basic problem is to try and figure out what are the transition matrices along the different edges in the tree. And this is important because, we care about how long these evolutionary branches are and all sorts of other properties of them. And of course, it's important for HMMs because that's the entire problem. So in fact, this is one other place where Jennrich's algorithm was rediscovered, is depending on who you're talking to, they might call it Chang's lemma. So in fact, that's what I thought it was at some point. I thought that was the original source of this algorithm, but it's not. You can trace it further back. And let me tell you the quick intuition for this, because this intuition will be very simple here, and it'll translate for us to all of the different models that I'll be talking about. So, the question is, I know the topology of the tree and I want to find these transition matrices R. Where is the tensor? What is the tensor that I can write down, that I can compute from data, whose hidden low rank decomposition is going to reveal to me the parameters that I want to learn, namely these matrices happening along the edges of the tree. And here's the idea, is we can reroute the tree arbitrarily, right? So imagine I give you a triple of nodes, A, B, and C, that are all extant. And what I can do is I can trace back their common ancestor in the tree. And eventually I'm going to find one node in the tree, which might be extinct, like in this case, which I can find 3 disjoint paths from that node, which in this case is Z, to each of the other extant species. Now I can treat each one of these paths as just a branch itself, because I can take the product of the transition matrices, and that tells me how the hidden state of Z affects the conditional distribution of A. But the important thing here is that A, B, and C are conditionally independent, conditioned on the hidden state of Z. And I claim that conditional independence is a low-rank tensor in disguise. That's the main point. This is maybe the second most important point in the talk. And if you get nothing else, I'll still be thrilled. So what do I mean by that is, imagine we're in the situation where I've reduced to the star graph, right? And the important thing is, when I look at the joint distribution of A, B, and C, that's a size of sigma by size of sigma by size of sigma tensor. Because they're conditionally independent, I can write out what that joint distribution is it's the sum over this latent variable of what is the symbol assigned to Z. And once you condition on what Z is, then you have an independent distribution for A, an independent distribution for B, and an independent one for C. And you take the tensor product of these vectors. These are length sigma vectors because they're conditionally independent. That's literally what conditional independence means. So what does this mean is that actually this tensor, which we can observe from data, is itself a low rank tensor. where each one of the terms in the rank 1 into the decomposition into rank 1 tensors is a different choice for the latent variable z that we can't observe because it's an extinct species. So that's it. And if you think about it, this conditional distribution is really just the columns of this transition matrix that I want to find. And that's exactly what Jennrich's algorithm lets me do, is it lets me read off the factors, not just find any old tensor decomposition, but find it uniquely. And you can just trust me that the notion of uniqueness sort of plays nicely here, that you can find these things in the right way. So this is an older work actually of Mossel and Rock that first did this. So they were the first ones to realize that you could use Chang's lemma along with this literature about how to reconstruct the topology of a phylogenetic tree to give an algorithm for learning these models. And what they do is they actually give an algorithm for pack learning. Yeah.
I have a question from Jordan. Please go on. One is, so it's low rank specifically because Z is drawn from a small finite alphabet?
Exactly. Because the rank is upper bounded by the finite possibilities for sigma. But to be clear here, we're assuming that the alphabet is the same at each one of the, both extant and extinct species. So in fact, when I have the size of sigma by size of sigma by size of sigma tensor, then you do expect to be able to use Jennrich's algorithm up to rank equal to the size of sigma. And there are actually extensions of all of these things that work in the case like in HMMs, where the rank might actually be higher than the set of observed symbols. And in that case, what you do is you go to higher order tensor decompositions, but things become more nasty because you don't have as clear-cut a conditional independence. I think it's a paper of Qingxing, Sham Kakade, and maybe Munzer Dale that does this, but I can find the reference. So for me, this Mossel Rock paper is awesome because, I don't know, maybe it was too early. So they proved it back in 2006. And, later on, about, 8 years later, people were still giving algorithms for learning HMMs. They just had forgotten that this thing existed and already did it. So, it's a very nice paper. I encourage you to take a look at it. One of my favorites. And actually, one of the things we can do is now let's put on our computational complexity hats. One of the things you might wonder is, Jennrich's algorithm needed a full rank assumption in order to apply it, right? Because it needed that the A sub i's and the B sub i's were linearly independent. Now, is this and the way that this manifests for us is that the transition matrices along the edges of the tree are full rank. And one of the things you might wonder is that just an accident of this algorithm that we have? Or is there a way to get around the full rank assumption? So it turns out that it is actually an honest to God barrier. So what Mossel and Rock did is, in the context of hidden Markov models, they constructed a noisy parity function. So it has some other degenerate properties that can let you get around it with higher order tensor decompositions. But at the very least, it is an instance of a problem in which the transition matrices are not full rank, and the learning problem itself is a computationally hard problem. In fact, people build crypto systems, things which are post-quantum secure, based on this particular assumption, which is the noisy parity assumption. It's an infamous problem in learning theory. I guess I'm not really going to tell you much about it, but it's hard. A lot of people think it's hard. The only person I met who thinks it's easy is Jim Simons, but I don't really know what the intuition is. And as I mentioned, it's actually hard to build. It's used to build crypto systems. So this was the first application that I wanted to explain to you. Was really the way that we used Jennrich's algorithm. Was we took our statistical model and we found a conditional independence. Now, it was important that it was not a pair of conditionally independent random variables, but it was a triple. That's what allowed us to use tensor methods which are unique under much tamer conditions than matrix decompositions. So this type of model is really enabled by the fact that I get 3 conditionally independent random variables. That's the same thing that underlies phylogenetic trees and hidden Markov models. Let's talk about another application that's near and dear to my heart, is a problem that comes up a lot in machine learning and data science, which is the problem of learning a mixture of spherical Gaussians. There's a long line of work on these things, but I'm just going to focus on the one part that's most relevant for tensor decompositions. So what is a mixture of spherical Gaussians? Okay, so you have a high dimensional Gaussian with mean mu I, and its covariance is going to be sigma squared times the identity. So it's spherical in the sense that, it's always a scalar multiple of the identity. So it really just looks like some kind of ball that's scaled. And the important thing is that you now have a mixture. So there are k different components, and you sample one of the components with probability w sub I, and then you take a sample from that Gaussian. So this is a very powerful model in a lot of applications because it's one of the canonical ways that we can think about generating data that can be well clustered. Because each one of these components is supposed to be a cluster of different types. So you're given a high dimensional data set. And one of the ways that you might think about finding the different constituent clusters is by pretending that it's a mixture of Gaussians and figuring out what the means are. So, the basic problem that we want to solve in this space is we want to reconstruct the parameters, which in this case are the mixing weights, the means, and you can even allow the variances to be different scalar multiples across different components, but you want to do it in polynomial running time and polynomial sample complexity. So that's the basic problem. And the way to think about this is that, what this problem really has in common with the phylogenetic reconstruction problem, the hidden Markov model problem, is that what makes it challenging is that you have latent variables. Here, what is the latent variable is when I observe a sample, I don't know which component generated it. So really, tensor decompositions have sort of led to this revolution within learning latent variable models. And there's this well-developed understanding now of how to create conditional independences or how to exploit it. This will be yet another example of sort of conditional independence in action. So there's a really nice paper of Su and Kakade that gives an algorithm that runs in polynomial time and sample complexity. It works when the mu i's, which are the centers of these Gaussians, have full rank. Now, actually, if you're precise, there are actually a bunch of parameters that you need in order to prevent the problem from being degenerate. So first of all, if the means are full rank but are very close to not being full rank, that would be a big problem. You would see it in the stability analysis of Jennrich's algorithm, which would then tell you that you have to take too many samples in order to actually get good statistical guarantees. So really the real version of this is you need a lower bound on the mixing weights. You need some sort of lower bound on the smallest singular value of the matrix that you get from collecting the centers for the different components. But the running time and sample complexity are polynomial in all of the natural parameters of this problem. So let me show you how to do their algorithm. In fact, that's one of the cool things is once you have Jennrich's algorithm, which again is actually not stated in their paper, you can do all of these things, even in a talk. That's very simple. So the main lemma here is, let's assume, just to make my life easier, that sigma squared is known, just for simplicity. Then the main lemma is that I can compute the following tensor using moments of my distribution. So this tensor would look like the sum over I of w sub I, which remember is the mixing weight, so that's a scalar, times mu I, tensor mu I, tensor mu I. So this would be great if I could do it, because if I could compute the left-hand side, this tensor t, then the factors in the unknown low-rank tensor decomposition would tell me the parameters of the model that I want, which is the unknown means. So I have to show for you how we can construct this tensor T from empirical moments of our mixture. And the idea is the same thing as before. There is some low rank tensor. It won't be quite as straightforward as last time, that I can compute from samples whose tensor decomposition reveals the parameters of a latent variable model provably. So what I'm going to do is let's just look at this tensor I want to construct, T, on the left-hand side. Let's look at the ABC entry of it. Right? Now, if instead I look at the output random variable x, which is a length n vector, because I'm taking a random sample from a spherical Gaussian mixture model, let's say that A, B, and C are distinct. So I don't have any repetition among these indices. If I look at the expectation of x sub A times x sub B times x sub C, well, what you can check is that it's really literally the ABC entry of this corresponding tensor that I want. This is because a Gaussian, you take it by choosing the center and then adding a random Gaussian noise to it, but that noise has expectation 0. So it doesn't show up in the expectation. Now, things are slightly more complicated when you have repeated indices. What if I repeat a single index? So A equals B, but that's not the same thing as C. So in that case, what ends up happening is that you're really taking a second moment of some coordinate. So you don't quite get the ABC entry, but you get some sort of extra correction term that depends on the variance of the noise that you're adding. And in this case, when you know sigma squared, you can literally correct what this thing on the left that you can estimate this third order moment is in order to get the ABC entry of the tensor that you want. Because I know sigma squared, and the other term right here is the empirical first moment of my spherical Gaussian mixture model. That's good. What's the remaining case? If A equals B equals C, you can correct it again. Not super surprising. And that's the proof, right? So now what this means is I can take moments of my distribution, which are things that I get from samples. And I can, figure out how to change those entries and, correct them in a way that I'll just be able to read off the entries of this left-hand side, this tensor T. And now I'm in business because, you can actually write it more compactly in the following way in case you're curious, and I'll put that on the slide later. But now all you do is you just use Jennrich's algorithm. That's it. And then you solve the problem of learning spherical mixtures of Gaussians. So you can do this exercise for lots of different things, which is that what's underlying the way that you use tensor decompositions in learning problems for learning latent variable models is all you do is you take some sort of latent variable model, and sometimes, the easy ones are sort of staring you in the face where the conditionally independent random variables are. Sometimes you have to do a bit more work to construct the right function of your moments to get something which is a low-rank tensor, but it can be done. You can do this for things like pure topic models, which are models for documents where you think about there's some sort of universe of topics that you could write about, and each topic is itself a distribution on words, and each document is described as a distribution on topics. So in these kinds of models, you can ask, when I give you a bunch of documents, which are samples from this model, can I learn the underlying topics that are important? And when you can do that, it paves the way for a lot of exploratory data analysis in different NLP applications and text analysis. But the same thing happens again, which is that you can write down a very simple third order tensor, which you can compute from data, whose low rank decomposition helps you learn the parameters of your model. You can even do this for things like community detection, where in community detection, what you have is you assume that you're given a random graph, but it's not an Erdős-Rényi random graph. Instead, it has the property that there's a hidden partition of the nodes into different communities. And you have different connection probabilities within and between communities. And then in this model, you get a single shot, which is a graph, and you want to figure out whether you can recover the planted community structure from that graph. Again, you can do it through tensor decompositions. These aren't the state of the art in terms of the best signal to noise ratio, but it turns out there what you do is you count different types of subgraphs. There are certain types of stars that you can enumerate, which again have the property that they have a nice conditional independence that allows you to use Jennrich's algorithm.
You have about 7 minutes to go.
Sounds good. So what I'll do is I'm just going to give a teaser for something that maybe I'll go into a little bit more later in the next time, but we'll see. So, I spent the talk trying to say that Jennrich's algorithm is this sort of, beautiful thing that gives you a wide range of algorithms, but there's still a lot more to be discovered. So let me give you one teaser about where I think one frontier is in this space, and it's really an algorithmic question. So one of the other things that we can do is we can ask to learn the parameters of a generative model, which now isn't going to have a discrete set of possibilities for a latent variable model. It'll have a continuous set of possibilities. So let me give you some examples, and this will be really a general class of problems that are called orbit retrieval. So there's one thing called multi-reference alignment. So imagine there's some sort of periodic signal, and you don't get exactly that signal, you get it with some noise. But then you have the problem that it has a random cyclic shift. So here, you again have this latent variable model plus noise, but what is your latent variable is the hidden shift. So it's no longer discrete because it's actually something that's, happening in a range of parameters. You can also think about, there are global registration problems that show up in signal processing, where you have the same type of thing. This is an image of Alan Turing. You add noise and you have, again, a random rotation. And one of my favorite ones, this is even a more sophisticated version, is something called cryo-electron microscopy, where you're trying to image different 3D molecules. And what you can do is you can prepare something that has a lot of copies of this molecule, and you get noisy 2D projections of the 3D image. But the big catch is that you don't know the orientation of the different projections. So now you're trying to learn from noisy data, but your latent variable is not only continuous, it's really coming from a non-abelian group because it's SO3. So orbit retrieval is this general class of problems that Afonso Bandera introduced me to, and they're super interesting. So what you do is in the general setting, you have, and cryo-EM is actually an even more sophisticated version of this where you add in projection, but let's not deal with that. So the basic idea is that you're specified by some sort of group G in a linear homomorphism. And what you get is there's an unknown signal X, and you get a noisy observation of that signal, but when you've chosen some sort of random group action, where G is chosen from the Haar measure on the group. And the goal here, you can't hope to recover X because, if I apply rho of G for some other G to X, I can't tell the difference between the original X and the thing after that, operation. So at best, I can hope to recover some X hat that's close to the orbit. That's why it's called orbit retrieval. And in our setting, if we think about what do tensor decompositions have to say about these types of problems, because we know that, moments are a very powerful way to get provable learning algorithms, we can do the same kind of thing, right? Let's forget the noise for now. It can be dealt with. It's not such a big deal. But the idea is that I can think about a new tensor, which is constructed in the following way. I have this hidden X vector, which is a dimension n vector. And now instead of summing over a discrete set of possibilities that represent my latent variable, I'm integrating over G. That gives me this tensor T on the left-hand side. This is now no longer obviously a low-ranked tensor. In general, it won't be. It will have high rank, but it still has some algebraic structure. Because, when I find a single vector X, what I want to do is not subtract a single rank 1 tensor from T. I want to subtract that along with all of its group orbits in order to reduce the tensor rank. So this problem is basically completely wide open. How to incorporate and marry tensor decompositions with algebraic structure, except for one tiny little result in here, which is, Alex Wine and I showed about 2 years ago that there's a polynomial time algorithm that works when X is random for the continuous group SO2. So that covers things like this continuous multi-reference alignment. And we don't understand really what to do for non-abelian groups. I have some thoughts, haven't been able to do it. But let me leave as a brief teaser in the last 2 minutes that what you can do is there's a way to use something called a tensor network, which is just a graphical representation of what a tensor is. So a third order tensor you would write with this sort of wheel with 3 spokes. And what you can do is you can use tensor networks as a language for manipulating tensors. So you can take 2 tensors, you can connect them along an edge, and that's really some sort of algebraic operation on what to do with those tensors on the other side. And it turns out that tensor methods play a major role in theoretical machine learning, statistics, what have you. And you can think about a lot of the previous works as coming from a very simple tensor network. Now, they don't say that, but if you look at their analysis, you can write down a tensor network to which you're using matrix methods like spectral techniques. And this is sort of a cornucopia of different tensors that have arisen. It turns out that you can build some sort of general strategy, which is, maybe I build a tensor network with some blueprint for how to connect different copies of T together. Then I turn that somehow into a matrix, and then I do something with spectral methods in the hopes that the leading eigenvectors recover the hidden parameters of the model I want to learn. The reason I'm telling you this is the way that we actually solved it for SO2 was we gave this monstrosity. That's a tensor network that's, so ugly that, only a mother could love kind of thing. And unfortunately, what we showed was that smaller tensor networks fail for this problem. This is literally the smallest tensor network that works. But, it goes to show you that at least there might be a very interesting marriage between, how to incorporate group structure along with tensor decompositions, but to use things like tensor networks as a sort of more general language for how do you go about designing good algorithms. Because it turns out that analyzing the spectral properties of the matrices that you construct in this way has a lot to do with solving combinatorics problems about counting labelings on these types of graphs. So I will stop there. There's a good chance I will never tell you about what happened afterwards and talk about something different, but I'll have to decide what I'm doing on Friday. So let me stop there and give you the quick summary. So what I showed you was, how tensor decompositions are unique under more general conditions than matrix decompositions. I introduced Jennrich's algorithm, and then I give you a range of applications to phylogenetic reconstruction, HMMs, mixtures of Gaussians. And, one interesting question that I think would be a lot of fun to explore is, are there more general families of tensor methods, in particular things that use some kind of group structure? So I'll stop there because I'm definitely out of time, but take any questions you might have.